Hi, welcome to online tutorial videos from JCBRO Labs. For more information and to download the model of this video, you can visit us at www.jcbrolabs.org. We also provide online training, online coaching, help in technical assignments. We also do freelance projects based on Matlab, machine learning, data science, Python, Raspberry Pi, embedded system, etc. So if you have any such requirement, then you can contact us at through our website, which is www.jcbrolabs.org, or you can also mail us at jcbrolabs@gmail.com. So in our last video we talked about DC to DC converter, and specifically we talked about a step down converter, which is also known as a buck converter, and we also simulated the same on Matlab. And then we talked about the PID control of the buck converter, and the link of those videos are given in the description of this video. Now in this video we'll talk about a step up converter, which is another category of DC to DC converter, and it is also known as the boost converter. So that means the output voltage which we will be getting from this DC to DC converter will be greater than that of the input voltage. Okay, so we'll be talking about mainly on the circuit diagram, and then how to find the parameters of this boost converter, and then we will simulate the same on the Simulink. So we will not go into the theoretical part of it, so you can refer any book for the more theoretical description of the same. Main motive is the simulation of the buck converter on Simulink. Okay, so or the simulation of the boost converter. So in boost converter, as we talked about, output voltage is greater than the input voltage, but for all this case, because they act as a transformer, so the input power is equals to the output power. So in that sense, if this relation has to be held on and output voltage greater than the input voltage, so obviously the output current will be less than the input current. So this thing has to be remembered. Now next thing, if we talk about the circuit diagram of the boost converter, then that is very much similar to that of the buck converters. There is only small changes into it. Okay, so let's go through it. So we have our input voltage here, and then in buck converter we were having a switch here, but in this case we will having a inductor, and then a switch will be here. So this switch can be realized with the help of a transistor or the MOSFET. So it's a high frequency switch, and the frequency is applied to it, which is also known as the switching frequency, and it is the input voltage. And then we have a freewheeling diode here, and then there is a capacitor at the output in order to remove the ripples in the output voltage. Okay, and here we will get the output voltage VL, right? So here it is C, so we can denote the current which is going through these ones, and here it is the inductor current IL, and this is plus minus voltage across it. Similarly, this output voltage, because as we discussed in buck converter, this voltage are specified for a specific kind of load. Okay, so we have to specify the load as well. So the voltage across it is the load, and here we have a switch. So here we apply a pulse width signal or PWM signal in order to change the output voltage across the load resistance. Okay, so it is a PWM wave. So main functioning of this C is to remove the ripples, or to so that the output remain within a specified range, because output goes like this. Okay, now coming to the normal working of it, it operates in two modes. One is continuous mode. Continuous mode means IL never becomes 0, and another is discontinuous mode. So our main requirement to operate this boost converter or an DC to DC converter is to operate this entire circuit in a continuous mode operation. Only then we will get the satisfactory value of the output. Otherwise, this output relation will not hold. Okay, so we will talking about the design parameters for continuous mode operation only. So for continuous mode, if while this continuous mode depends on various aspects like switching frequency and load resistance, etc. So we are assuming that frequency is enough so that we are operating this boost converter in the continuous mode. Okay, so here the output in continuous mode, output is given as the input voltage divided by 1 minus D. Okay, where D is the duty cycle, and which is equals to D equals to 1 by F, where F is the frequency of the or a switching wave frequency or PWM frequency. So D is always less than 1, so this particular quantity will always be less than 1, and the output voltage will be greater than the input voltage. Okay, so from here, if we have specified like the amount of output voltage we required and the amount of V in. From here we can identify what should be the duty cycle of the wave. Okay, this is wrong. Duty cycle is not 1 by F, sorry for that. Okay, duty cycle is equals to T on by total T. That means T on by F, or T on into F, because 1 by T equals to the frequency. Okay. Sorry for that. Then the inductor values. Another thing is the what should be the inductor values. So if no load condition is specified or the specification are given in terms of the ripples in the inductor current, right, then the inductor value can be given by this particular formula: L equals to V input into D divided by delta IL into frequency. Okay, so that is the case when our specifications are given in the terms of the ripple current. Okay, so this obviously this delta IL is the inductor current variation. So it is not necessary it is always given into that. We can also have the minimum value of inductor for a given value of the load resistance. Suppose we have been given this like 50 ohm load resistance is there, and we have to design boost converter for that. So the minimum value of the inductor for which this entire boost converter will remain in the continuous mode is given by this particular formula: D into 1 minus D square into load resistance divided by twice of F. So similar to the buck converter, it is not like for the boost converter as well, it is not like the input output relation will hold good for any value of R. Okay, so it puts a limitation of R. So you can think of if we have defined the L, then we can find the maximum or minimum value of RL. Or let's say if we have defined the R, then we can define the minimum value of L. So the L must be greater than that value. Okay, so you can think of it in either way. Now another one is the capacitor value. So the as we talked about capacitor value, it is mainly for removing the ripples. So the minimum value of the capacitor is given by the ripples, allowable ripples in the output. So it is given by d divided by RL into del V out divided by V out into F. Okay, so from this value you can identify the minimum value of the capacitance required for the required boost operation. Okay, so these are the main parameters which needs to be calculated for simulating boost converter. Now let's take an example. This is how the specifications are given. Output voltage required is 30 volt, and the input voltage is, let's say, 12 volt, and we need a load resistance as of 50 ohm, and then frequency is 25 kilohertz. This is the sampling switching frequency, and it has been given like this output ripple voltage. Output ripple should be less than 1%, which indicates that means the del V out by V out should be minimum or should be less than this 0.01. Okay, so this is how our specification can be given. So based on that we'll obtain the various parameters. So first thing is to obtain the D. So D can be obtained simple by this formula, because V out equals to V input divided by 1 minus D. So D can be written as D equals to input voltage divided by the output voltage, and it comes out to be 0.6, right? Very straightforward. And then the minimum value of L can be given by this. So L should be less than greater than, because in this case RL is given, so we can write it D into 1 minus D square into R divided by 2F, and it comes out to be 96 microhenry. And then we can identify the value of C. So C should be greater than this value, which is given by D divided by R into del V out over V out, which is the ripple, into F, and it comes out to be 48 microfarad. Okay, so C, if minimum 48 microfarad, then we will get the ripple of 1%. So if it is greater than that, we will get less ripples as well. Okay, now we can also identify the value of inductor current, or in our case the input current, that is simply Vs divided by R into 1 minus D square, because it is V out divided by R, and it comes out to be 1.5 ampere. Okay, so these are the very small calculations which can be done. Now our next task is to create, or is to simulate the same on Simulink with these particular values. Okay, so let's open Matlab now. So let's open Matlab and go to Simulink. So what we'll do, we will we will create a new model. Okay, and first thing we'll do, we'll save it so that we don't lose our data. Okay. So here, boost converter. Okay, and then let's save it. So let's search the requirement. First of all, we'll need power GUI. So this power GUI is required to simulate the power sim-space objects. So you have to be very careful, like sim-escape objects and sim power system objects, they are not interconnected. Okay, so if you are selecting the power system objects, then all objects must be of power system only. Okay, now we will need a voltage source. So voltage source. So here we have DC voltage source. Okay, and then we need because we want to plot it, so voltage measure, that means voltage measurement. this has to be done. Okay, and then we need our resistance, so we need RLC branch. Okay, series RLC branch, we can convert it into 3 parts, and then we need a diode. Okay, so we can have a diode here, and then we need a switch, ideal switch. So instead of this switch you could have a MOSFET or anything, so we are just having this switch. Okay, this is not that one. The ideal switch is there. Yep, here is the ideal switch. Okay, so now let's make it. Okay, let's zoom a little bit. So first of all we need 3 such branch for R, L and C. Okay, first we'll convert it into an L. Okay, so only L is there, and the value of this inductor is 96 microhenry. Okay, so let's set to it micro 10⁻⁶, and here it should be 96. Okay, okay, that's done. Okay, now we need connections. Okay, and this switch has to go here, so we will rotate it, rotate and flip. It should be rotated in counterclockwise direction here. Okay, here, here, this switch goes here, and then this has to be capacitor, and the value of capacitor is 48 microfarad. Okay, so 10⁻⁶, it's already there, so we'll convert it to 48. Okay, now let's connect or rotate it in the clockwise direction. Yep. Okay, change it to C only and change it to L. Yep, and then connect this diode here, and then it has to be connected to the R. So we have a specific requirement for load resistance as a 50 ohm, so we'll check 50 ohm only. Okay, it has not been set, only R. Okay, and change it to R, and let's rotate it in the clockwise direction. Okay, now it's done. And it has to be connected here. One point should go here and here. Okay, fine. And here we have a voltage measurement, so we'll connect it like. Okay, so we want to calculate the voltage in numeric form as well. Okay, so what can we do? And graphical form, we want in graphical form as well, so we can select a display, and here it is, a scope. Okay. Okay, it will be connected here only. Okay, fine, let's save it, and we'll do the simulation for 0.01 because it will run very slow. Okay, now change the value of this DC voltage. The input voltage was of 12 volt, so from 12 volt power supply we are going to get 30 volt at the output. Apply. Now we need to apply this clock frequency or the switching frequency. Good, and for that we need square or a pulse generator, and this pulse generator will be, okay, let's drag it to upper side. Okay, So this pulse generator, and its amplitude is 1, and the period of this pulse, this is the frequency percentage of it is 60%. So let's change it to 60. But the period, it is 1 divided by 25 kilohertz. So 1 divided by 25 kilohertz equals to, it is 0.00004. So 0.00004. Okay. So this value has to be critical, because this from this value we only determine the value of C and L. Okay. So now everything seems to be fine. Let's connect this pulse generator to the gate, and let's finally save it. Okay, that looks fine. Go to scope and let's change some properties of it. If you want to visualize the complete graph, set this limit, remove this limit, and in general we will increase the line size of the graph. So let's make it 2. Apply. Okay. So now let's simulate it. Remember, we are simulating only for 0.01, and if everything goes fine, it will simulate. It's compiling. Okay, so the output voltage we are getting very close to 30. This is 29.4. We can find the expected, or can calculate the approximate error as well. And if we look at the output, yeah, output is going like this. So it is having some overshoot, and then here it is. Okay, so we can zoom it up uh, with the horizontal zoom and vertical zoom only. That is, let's first zoom y-axis, and then let's zoom the x-axis. Okay, so this is what I was talking about, the ripples. So if you check the ripples, so ripples are nearly, because it is 0.4, near about 0.02 or 0.2 ripples are there. Okay, so that is how we can simulate it. So let's change the certain values of it. Let's say, because this was the minimum value which was required, so let's say if I have a 100 microfarad capacitor, and let's say what happens to the ripples. Yeah, you will find now ripples are less, and it is more close to the 30 volt. And if you auto scope, yes, you can visualize the value of ripples as well. So this is its settling time. It is nearly taking 0.09 second to settle. Okay, let's we can simulate it for a little longer. So let's say 0.03. Yeah, so this is finally settled value here, and we can zoom it in y-axis, and then we can zoom the x-axis. Yeah, so now the ripples have been reduced. So this capacitor is used to reduce the ripples. Now let's change the value of this L, or let's change the R first, and then let's see what happens to the output voltage. So if we increase the resistance R, okay, so you will find it is no longer the same value of 30 volt. Okay, so there is a limitation over R, because L is determined by the R. So if R is changed, L has to be changed, or you can think of it vice versa. If L is fixed, that means this particular the fixed value of L put some restriction on the allowable range of this load resistance. Okay, so let's try to change this R to 10 ohm. Okay, and let's see whether it works. Yeah, it is working nearly, but less. Okay, let's change the value of R. So ultimately we can say this L minimum value puts the maximum limit on this R, but when R is reducing towards the lower side, further lower side, again this relation is not holding good. So we can think of, or you can try it by yourself. So if you try to make a plot of this R and L, you can think of it is varying like this one. Alright, so here we are increasing or decreasing value of R. So, and here is the output voltage. So it is like this. Okay, from here within this particular range, this R will work satisfactory, but at this range, the output voltage may go beyond the safe limit. So this is how we need to reduce R. So if in any other sense, if R is increasing, right, R is changing, so what should be changed? We can change or we can make it again to the 30 volt by changing this frequency. Okay, by changing the duty cycle, because if we go through the formulas again, this value is also depending on the D. So if L is changing and we have this L minimum is constant, right, so the output this can be changed by changing this value of D. Okay, because R and L also depending on the value of D. Okay, so there is a relation by doing this change. Okay, there is a relation of duty cycle in order to incorporate the change in the load resistance into the output voltage. One thing, here comes the analysis of the next part. Okay, so now if we want our system to adapt automatically and to give the fixed value, so we have to make it a closed loop. Okay, so let's say we have a boost converter here. Okay, not the boost directly here. We can have a PID here, and then we can apply a boost converter, and the output of this boost converter, because this was here, that is subtracted from the reference voltage. So we can set our reference voltage here, and it is changing the duty cycle of the boost converter. So if our reference voltage, let's say 30 volt, and so we want to obtain only 30 volt at the output. So this PID controller, if there is a change in the resistance, load resistance, so this PID controller will automatically change this duty cycle so that output voltage remain at 30 volts. So this is the closed loop implementation of this boost converter. We can say closed loop implementation. Okay, so in our next video we will talk about how to implement this closed loop PID controller for boost converter. Okay, so I hope you understand a lot, or I hope you understand how to design and analyze a boost converter in Simulink. Okay, so if you have any doubt or any question or any suggestion, then you can let us know by commenting below this video. Okay, finally we also provide online training, online coaching classes, help in technical assignments. We also do freelance projects based on Matlab, machine learning, data science, etc. So if you have any such requirement, then you can let us know by contacting us through our website, which is www.jcbrolabs.org, or you can also mail us at jcbrolabs@gmail.com. Okay, so that's it for this video. Thank you.